All right, let's get started.
Why is it like 1.2-1? Like homework problem is 1.3-2.
Yeah.
Like what is that?
That's the homework number.
1.2 problem number 1, 1.3 problem number 2.
Yeah, there are different sections. So the book, if you look at the book assign homework by sections. So that's 1.2, meaning the section chapter 1 and section 2. And there's several problems. That's the first problem, right? So there's 3 digits there for all the homework numbers. Okay, so last time we talked about what's the internal force. And so basically, when you look at an object, you want to find out the inside, locally, what's the force there. And you make a cut, you find the force there. That's the internal force, right? And then we define stress and strain. So it's basically the intensity. And stress, you look at an area, when you cut somewhere, there's that area, total force, and then divided by the area, that gives you the stress. All right. So then the next question we want to continue to discuss today is, what's the relation between the stress and strain? Right? And how is it related? Of course, that's including normal stress strain and the shear stress strain. All right. So this is how you determine. So many of you took the material engineering already. So I'll be very brief here. If you haven't, that's just a nutshell of what we need here, right, in this class. So you may need to review a few things related to material engineering about mechanical property of material. Okay, so how to get a stress-strain relation, right, for a material. Basically, what we do is we get a piece of material, and then often you cut into a dog bone shape sample, right? Then you do a stretch. You stretch it on both ends. Then the middle part, the uniform portion of the sample. So here, this portion, that's what we use, will generate a uniform deformation field. Because we know in here, anywhere you cut it, right, based on equilibrium from last class, we know you'll get the same force everywhere, right? So it's uniform. And therefore, that uniform kind of magnify. You don't want to measure 2 particles very close. It's hard to measure. So that uniform field gives you a big enough field. You can measure how much elongation is generated there, and then how much force is applied there. That's equal to the force you apply to your device, right? So from here, then you can plot this force versus the deformation. And deformation, we say, okay, how much this point going to elongate, delta. So you get the pressure, the force, and the deformation relation. And depending on material, you may get different ones. I know you must test on metals, so you'll get something like this. And then it will eventually break down here, right? This is a type of metal. For different metal, even the same metal, if you have different pieces, you may get different curves, right? So depending on what you tested. In material engineering, have you ever tested other materials rather than metal? Fibers or plastic, right? Or let's say you test a fiber or plastic, you'll get something like this way, right? Just round up and go fill, right? Or if you test a piece of muscle or arteries, what do you get? You get something like this way, right? So depending on the material, they have all different properties. That's why you look at the material engineering, look at the different materials. Okay, here we mainly limit ourselves to metals, engineering material. We're not talking about the muscle or bones, right? So you don't need to worry about this kind of curve, right? Now with this, you get the load versus deformation. As I show here, let's say I have 2 different pieces of the same material, right? One, you may get this one, the same material. Then this one, another material, you may get this one. So each pieces of a sample, you get all different curves, right? So it's all depend on the material. I mean, the sample you put there. So how can you somehow get rid of this dimension and to get the character of the material itself that doesn't depend on your size? How can you somehow normalize it? you can divide the area, for example, right? You can use stress instead. So what we can do is, based on our definition, you calculate the stress, that's P over A. Then you calculate the strain, and that's delta over your initial length. So this way you normalize. So you make it non-dimensionalized, right? And once you do that, you get a curve like this one. And now, if you have the A1 sample or A2 sample of the same material, you get the same curve. Okay, so it's material dependent rather than all the sample dependent. So this will be something you can uniformly use it. Let's say I'm using metal, you're using the same metal, then we should have the same curve. So this way I can talk to different people we get the same thing, right? So therefore, this will be more representative of the property of the behavior of the materials. That's why we use StressStrain curve to describe it. All right. Okay, now this is a typical metal curve we know from previous course. Now, from here, what's the relation between stress strain? It's this curve. This is the relation between stress strain, right? You give me a strain, I can find you the stress. You give me a stress, I can find the strain, right? So this is a relation, but this is a very nonlinear relation, right? And in the small deformation range here, right? Within this range, we see here this portion is very linear, right? So it's a linear part, and we like this part. It's a small deformation. It's easier, linear, right? Linear equation. So stress is proportional to strain in this range. And in this class, we always talk about this range. We not talk about the nonlinear plastic range, right? Okay, so in the range we are considering the small deformation, small load range. What's the relation between stress and strain? It's linear or proportional. That's the same word, mean the same thing, right? So we have a stress-strain relation in this range, right? So that is actually my next slide. Okay. So before I move to the show this relation equation, now the few key points. Let's just review what you learned before. One is called ultimate stress. So this point, how much is the high stress you can go for this material. Another one is the yield stress. This is the point. So we always use this our limit. So you never design anything that stress go beyond the yield stress, because that's what we consider failure, right? Okay, now this linear relation, if you put it, so this here is the equation. And actually, there's some guy hundred years ago find it, and he was the first one. So we name after him, right? If you find something today, maybe 20 years later, people will name it after you. That's the way we do it, right? So we call it Hooke's law. And so Hooke's law basically means stress is proportional to strain. And they're proportional, right? So they are linear. You can put it other way, right? And also there is a ratio here, the modulus. We call it modulus because it shows how stiff the material is when you deform. So this is a ratio, right? E is a ratio, sigma over epsilon. And this has a name called Young's modulus. See, another guy. It's not an easy task to find this one equation. Two guys contributed, got the two named after, right? Put all this in here. So Hooke's law, but the ratio is called Young's modulus. All right. Yeah. Capital E is capital L. It's capital L. I don't think I think in this textbook we use letter E, capital E, as a Young's modulus. Yeah. Different textbook can use different notations, but in this book, E stands for the Young's modulus, and sigma always stands for the normal stress, right? Epsilon always stands for the normal strain, right? Okay, now, what about the shear? Similar, right? When you have a material, you try to, for example, we have this block of material, right? You put it attached to one side, and then you apply force V here, right? You can generate deformation, and then you can plot the V versus what the displacement here, delta, right? And then you can convert that to the stress, tau versus what? Versus gamma, right? Shear strain. the angle change. So this is the gamma. Okay, and you'll get something similar kind of curve. And we'll talk about the linear range again, the same. So you're going to have this one called tau y, yield shear stress. And we'll talk about within this range, then you have this linear relation. And this actually don't have a separate name. It's the same Hooke's law, including both normal and the shear. Right? And later on, we're going to talk about the more general 3D situation. So they all call Hooke's law. As long as it's linear relation, you call Hooke's law. But this G, not called Young's modulus anymore. We call shear modulus. And it's not named after anybody. It's just shear modulus. I guess too many people use this one, contribute to it, right? So there's no special person go after. Okay, and quickly, there's a relation between normal stress and the shear stress, normal strain and shear strain. And in the textbook, there is a section describe it. So I leave that as after class reading. And just very briefly, here is a key equation, connect the modulus, right? The shear modulus and the Young's modulus, they are connected this way. Now, what's the mu here? Nu, right? I think they call it nu. Nu is the Poisson's ratio. Okay, what's the Poisson's ratio? All right. Yeah. So by definition, it's when you stretch something, okay, you will actually get a rubber band. If you have a rubber band, stretch it, you will see the length get longer, but the lateral cross section gets smaller, right? So the Young's model, the Poisson's ratio describes this phenomenon. So it's the shrinkage in the lateral direction versus the elongation strain in the axial direction. That ratio we call Poisson's ratio, and that normally, you know, when you have a material, you stretch it, this will be a long elongation, right? So let me write the equation here. The nu will be equal to the epsilon in this axial direction versus the epsilon x. Let me put it x, y. So the y will be lateral. So this is the, let me put it this way. So this is the epsilon x direction, and then this lateral direction, that's the epsilon y. Right? And when you stretch something, this will be positive, right? So this part is positive. And then this shrinkage will be negative, right? So they want this ratio as just a positive number. So oftentimes you see the definition put a negative sign there. They basically say that's a positive ratio, right? And for most of the materials, this thing change in a range. So actually we're going to discuss in chapter 7 about the range of Poisson's ratio, right? But for most of the material, it's changing from 0 to 0.5. That's the range. And what's 0.5? 0.5 is like for tissue. For muscle, for things that are not changing the volume when you stretch it. They keep a constant volume, and then the Poisson ratio is 0.5. And there's a section here. So I leave this part. It's very fun to read it. So read the textbook. All right. All right. So I want to give more time to the key question here is safety. Now we talk about the load. We talk about the internal force. We talk about stress and strain. Now, how can you make a structure safe? That's a general or key question when you do engineering design, right? Okay, so here I list a few things. You can make it safe by limiting the load. Don't put too much load on it, right? That's common sense. Or you make the structure bigger. Instead of a one column thing, you make it huge, right? Then you'll be safe, much stronger, right? You waste more material maybe, but it will be safe. Right? Or you change the material. Instead of use rubber, you use steel. Then you can stand for more load. Right? Or you can control the deformation. Right? You allow it to deform a little bit, but don't deform too much when applying the load. Then it's safe. Right? So you see here, load, structure, and material. Right? So if for any structure you have to check everything, then you have to check, let's say, 3 or 4 things. Right? But are these related? Are the load related to the structure, related to the material? Let's say load versus and the dimension. How much load you can put on a structure? Does it depend on the dimension? Let me put it this way to be safe. Yes, right? You have a bigger structure, you can put more load. So But how you control it? You may want to control the ratio, right? What's the ratio between load and the dimension? Between load and the dimension, size, load versus size, what's that? That's like pressure. That's stress. So basically we can control stress, right? So if you have, let's say, if you have, this is actually the same I just said. Okay, if you have a load, let's say you have two structure, right? So one you may load this way. So you remember I just draw this curve. You have this kind of deformation. You have two bars, you stretch it. And then you have another bar, you stretch it, you go this way, right? So this will be the A1, this will be A2, right? Instead, you check individually, say how much load you can go here or here. You can use the stress. Once you use stress, this actually becomes one curve, right? Stress, strain. And then you have just one curve and describe it. So you can do two ways. For each structure, you make sure their load is within this limit, right? You have to check all 10 or 100 different structure. Or I can say, oh, just use the same material, so therefore I just check each one's stress. Make sure their stress is not over here. Then it will be safe, right? So as a general principle, which one is easier to say? Second one, because you just say, okay, stress has to be within this limit, yield stress, right? So therefore, we oftentimes use stress to describe. Yeah.
Could you give an example of like a beam that's like undergoing something in real time, like what this graph would represent of what's happening with the beam?
Mm-hmm. Yeah, we're going to have example. I'm trying to first present the theory, then we'll go over a couple of examples. How you use this theory to actually check on a structure, right? So I have two structures we're going to talk about. All right, so to limit it, we said that you have to limit stress, right? Okay, so now another concept is, okay, so here's a stress-strain curve. So for the material, I have to limit it. Definitely, I don't want loaded over here. That's my red zone, right? I don't want to go beyond that. But the question is, if let's say I design a chair or a car or a bridge, right? If I use this limit, sigma yield, I want to make sure no piece of this bridge beyond this yield stress. So let's say the yield stress, we'll just randomly give a random number. For many metals, it's like a 200 megapascal. Okay, let's say the yield stress is 200 megapascal. Now, can we design a bridge, right? All the pieces, when I have 10 cars on it, it will be, let's say, 190 megapascal or 199 megapascal. It's safe, right? It's 200 limit. I'm at 199. So I'm safe. But is it safe enough? No. So it's not safe enough. So when you design structure, you want to keep some extra space there to be safe. If someone jump on it, right? Have a music on the car, shake a little bit, and then you don't want the brake to fall down, right? So therefore, you want some safe space. Okay, how can you ensure a safe space? You want to say the stress don't go to 200. Maybe go to 200, go to 100, or maybe go to 50, or go to 150, right? So you want to ensure it's safe enough. And that safe enough we call a safety factor. Okay, for example, when I design this bridge, I don't want the stress go to sigma y, 200. I want to be maybe half of it or a quarter of it. So you basically calculate the stress. Make sure your stress is smaller than the sigma y divided by a factor n. And that n is the safety factor. Okay, so it's easy to interpret what's a safety factor. So it's basically how many fold you want to reduce your maximum load, right? I want to reduce 2 fold, then the safety factor is 2. So, okay, so therefore, for different structures, you can give a different safety factor to make sure it's safe. For example, if you design a chair, you can maybe just give a safety factor 2. That should be good enough. You bump a little bit, it will still be okay, right? Even if it fails, it should be not a big problem. But if you design a nuclear reactor, you don't want just a 2, because something happen a little bit, it break, then it's a disaster, right? So for nuclear reactor, you may want a safety factor of 10 or 20, and that's what actually people are doing. So for different structure, based on your knowledge, your experience, right, and the history, you can give different safety factor. That's how you control a structure to be safe. Okay. All right. So now, when you do a design, okay, how do you calculate how much stress you can give? You will basically calculate this stress, what we call sigma. Actually, I think it's next slide. So the allowable stress. And here is the equation. Okay. So we calculate this value of we call allowable stress. Basically, that's the limit for my design. It's not the limit for the material. It's the limit for my design. Right? When I design a structure, I want the stress to go not beyond this value. All right. So it's basically the limit of the material, you make it n-fold less. And not n is called safety factor. All right. Okay, is this easy to follow? Okay, it's easy to follow this way if I explain this way. But when you actually solve a problem, sometimes people get confused. They do the wrong way. Make it bigger or make it small. Okay, so let's use a couple of examples to actually explain what you have there. Let's see what I have here. Okay, so when you design, that's just general principle. You want to make sure the stress is smaller than that, right? So let me find a blank space. So yeah, here is one space. So I'll use this space. Okay, let's say I want to design a bar. We'll start with a very simple example. Okay, I'm just start a cable. Let's say I put a cable, put a lamp there, right? So I want to hang a lamp on the ceiling or hang something on the ceiling. So basically a bar. That's what we have here. And the load is known, right? Okay, so I know the material. Let's say sigma y. I know. I can give, let's say, use the example I just gave, 200 megapascal. It's a very strong metal, right? Okay, so let's say how safe you want to be. Give a safety factor. 40? For hang a lamp, you need 40 safety factor? No, you don't need that. 4. Okay, so n equals 4. That's safe enough, all right? Okay, so now, okay, we can answer two type of questions. One is, okay, I know the weight of the lamp. Then I design a cable. How big is the cable I need to buy, right? What type of cable? That's one way of a design question. Another way is, let's say I have this cable. I need to find out how much load I can put there. Right? This all can be designed, right? Make it safe. Okay, which one you want to go? Select one we'll do first. Second one. So I have a cable, right? Let's say I have a cable. Length equals, let's say, 2 meters long. And the area, cross-sectional area, give an area. Let's say I'll just put a simple number, make it easy to calculate. Let's say 2 millimeters square. So it's a very small wire, right? 2 millimeters square, the area. Okay, now I want to find out how much load I can apply in there to make it safe. Okay, how can we answer this question? How to start? Yeah.
You said maybe like a constant force that you expect.
Okay, so constant force, right? Is it a constant force in this cable? When you have this, say right now I'm drawing this way, right? It's like in the example I'm saying is this way. So you have a weight here, and this is the weight. This is the same thing, actually, right? Now, when you apply this load, what kind of force you have in the cable? First, you need to find out what kind of force you have in the cable, right? Can we find the force in the cable? How do you find the force in the cable? In the cable. You make a cut, right? See what we learned, now we use it. So you make a cut somewhere here. Once you make a cut, then you select a free body. Draw the free body diagram. Okay, which part you select? You can select the top part or bottom part. How about we select the bottom part first? Okay, let's select the bottom part. So here's my cut. Here is the cable line. And here is the weight. And here is a load P. Remember, this is the cut. This is not the wall. All right. So now, is this complete free body diagram? No, there must be a reaction. So our guess will be an N. I'm not sure, but I guess there is an N. And so because I'm guessing, so I put it as a positive direction. Remember the positive sign away from the surface, positive. All right. Okay, is there any movement? Shear? We show there will be no, right? Okay, so that's it. That's only load and the reaction for this free body diagram. So it's complete. So you have this free body diagram. Now write the equation of equilibrium. What's the equation of equilibrium? You have to set up an x direction, right? Either way. X direction up. Okay, I saw time up. Okay, so I have positive n, then minus p equal to 0. Okay, so what's n? N equals to p. So I know, oh, in the wire, basically the force in the wire will be exactly the force, the weight of that lamp. Okay, so, but that's what we're looking for. We don't know yet. We try to find out how much weight the lamp can be, right? Okay, now we find out in the wire, this is the one. Okay, now what's next? N over 2. Okay, why n over 2? What do you try to do?
That's pressure. Force per cross.
N over 2. What's n over 2? What's a 2? So what do you try to do next? Because we have too many 2's here. This is 2. This is 2. You have to tell me which 2 you are putting there. Let's change the numbers. So make this 3. So you don't have different, don't have the same number. Okay. So what do you try to do? N over 2. You try to calculate the stress. Okay. Here we don't call it the pressure anymore. We call it the stress. All right. So we calculate the stress. So sigma will equal to the n over the area A. A is 2. Right? I put the letter this way, make sure we clearly understand it. So that basically is n over 2. All right, so now I calculate the stress. You say, I don't know the value. That's okay, we express it, right? Yeah.
You have the area in millimeters. When you convert that to millimeters squared, can you convert that to meters squared?
Yes.
Just express it as newton.
Yeah, yes. So you should have 2 times 10 minus 6. That's it. Right? Good comment. All right. So we have stress. Although I don't know the value, but I know its stress should be calculated this way. Now what's next? How can I make this safe? I want to make this stress smaller than what? Should be smaller than the allowable stress, right? That's what we define. Okay, now what's the allowable stress? Let's ignore this one. What's the allowable stress? It should be sigma y over n, and that is 200 over, what's the safety factor? 4. Okay, what's the value? 50. So we know you want to make sure your stress is less than 50. Right? Okay. Now, how can I make the stress less than 50? Do we have enough equation to find the answer?
Is that equal to 49.9?
Yeah, so you have here. So when n over a, actually we know a, right? So let me just write down n over 2 times 10 minus 6. This is the stress. We want to make this one smaller or equal to 50. Now can you solve this one? Find out the n. N equals what? Something of 100, right? 100 times 10 minus 6. Right? Is that correct? Is that correct? Right? So basically here, let's use the equal sign. You can use the equal sign. Right? So n equals to 50 times 2 times 10 minus 6.
Equals 0.0001, or you just express that as 10 to the negative.
Okay, so we can only apply, let's say this will be, let's say 100, right? 100 times 10 4, 10 6. So therefore that equals 10 minus 4. So you can only apply this little stress, a little load there. Why is so little? Why so little? Something wrong. I know I want to tell you something wrong, but You guys find what's wrong? The unit.
Yeah,
Megapascal. You mix some other thing, right? So this is a megapascal. So here is a 10 what? 6. That we ignore. Remember here, you remember the 10 minus 6, but here is 10 6. So these two actually will cancel out. So what's the answer should be? 100 Newton. Right? 100 Newton. So we can apply 100 Newton lamp with, we can hang with this cable. Be safe with a safety factor of 4. Right? Okay, 100 Newton, that's what? Like 100, that's like a 10 kilogram. 10 kilogram, that's what? 20 pounds, somewhere around 20 pounds, right? So that's how much the weight can be. All right. Any question about this process? Okay, now I want to twist this question a little bit. Just say if you can twist your mind, kind of answer the question. Okay, remember now we have n equals 4, right? And the A equals 2 millimeter squared. And the load we can apply, the weight is 100 Newton. Okay. Now, what if I apply a load of 200 pounds there for the same cable? Okay, for the same cable, same material. Now I'm just carrying 200 pound weight. What's the safety factor in this case? What's the safety factor in this case? That's my question.
Pretty small.
Pretty small or smaller. If you hang a weight of 200 Newton with the same cable, what's the safety factor? Okay, let me generate a new piece of paper. Let's say, oh, let me create a new page so we can talk about this one. Okay, so that's the one we just solved. Now I have the question is, I'm applying, okay, n equals to 200 Newton. That's the different question now, right? Different problem I'm trying to solve, the related. Okay, so I'm applying a 200 Newton force lamp there. Okay, I still have the same cable, so the A is still the same, 2 millimeter. Okay. So my question is, what's the safety factor of my structure? This structure, I'm building this cable, right? 2 millimeter, I'm carrying a 200 pound there. Okay, so now my question is, how safe is this one? What's the safety factor? I ask you to determine safety factor. How do you answer this question? Solve this question?
It's 0.4.
0.4? No, I can tell you no. The answer is 2. Okay, but let's see how you solve it. How do you find the safety factor? That's basically the question, right? Okay. What's the safety factor? It's the yield stress versus the allowable stress, or versus your working stress. Okay, what's the allowable stress? What's the yield stress first? The same material, so yield stress should still be 200 megapascal, right? Now, what's your working stress? When you hang 200 pound there, 200 Newton there, under this cable, what's the stress? So it'll be N over A. What's the value? Is it 100? 100? What's the unit? Megapascal, right? If you don't believe, calculate. Say 200 Newton versus A, that's 2 times 10 minus 6. Another minus 6 flip over, become megapascal. Right? Remember before, when we hang 100 pounds, what's the stress? think this way. When you hang 100 pounds, what's the stress? Last time, that's the question. 50, right? What's 50? So when you hang 100 pounds, this stress is 50. Now I have 200 pounds, double. So you should get a double. You think this way, you don't need a calculator, right? Okay, so you get the stress 100 megapascal.
100 pounds or 100 newtons?
No, stress. No, this is Newton.
Yeah,
200 Newton. Yeah, sometimes maybe verbally I said wrong pound, but it's Newton. Right? Okay, so now I calculate in this cable, if I hang 200 Newton weight there, the stress will be 100 megapascal. Okay, now what's the safety factor I have here for this structure? So the N should be sigma y. The material can go 200. And now you're at sigma, at 100. So the safety factor, therefore, I have is equals 2. If you don't believe it, let's check on it. Okay, so what's the sigma allow for this material? If I have a safety factor of 2, what's the allowable stress? Equals 100. Right? Sigma y divided the safety factor of 2 is 100. And sigma, say 100, 100, this is the same. That means if I apply load at 100, I have a safety factor of 2. Okay. So now, just a quick summary. Okay. So when I give you a structure, I can ask you questions many different ways. I give you the material, give you the cross section, ask you to determine how much load I'd be able to apply there to reach a safety factor of 4 or something, right? So ask you to determine the load. That's one type of question. It's a design, right? Or I can ask you, okay, check on this structure I designed. What's the safety factor? Is it safe enough? So check it's safe or not. That's the second question. Third question is, I give you the load, and I give you the material. I ask you to say how big that cable is supposed to be. You find out the A. That's the third type of question, right? And I don't have time to go over that. And your assignment to try the same problem. Say if I want to put a load of N equals to 500 Newton now, okay? I still want a safety factor of 4. You design what's the A supposed to be. Tell me what's the A, right? You can tell me next class. So basically you just try it. I just want you to be familiar with all the 3 type of questions because that's engineering problem, it's all come up. And the homework problems, it's all come up. All right? Okay, any questions? Questions? No questions? So clear or so confused?
A little bit of both.
A little bit both. So what's the confusion part? Ask that part. Let's put this.
The graphs and just like the concept of what shear, stress, and strain like are.
So that's all the concepts. So you just have to read the. My suggestion is you can view the video again, right? The video is actually already remade and posted on the YouTube. You can view it, and also read the textbook because there are lots of definitions. Don't read it. I'm not ready to dismiss yet. So read the textbook. They give you in verbal, clear language, define it. So you read it, help you clarify the concept. It's very critical. You know all this concept, so to be able to move on. Yeah.
How do we find you on YouTube? Just type in your name.
Just type my name and then YouTube together. You will see it. Okay. If you need to send me an email, I can send you the link. Yeah.
Are you going to open up next like fatigue and creative? Like heat stress and
Freebody, that we not talk about that. The different way of damage. Okay. Don't collect your note yet. Okay. So I want to use a 5 minute go over another example. All right. I think example is critical. It's important. So you'll be able to use it to do the homework. All right. Okay. So my next example is we have this rigid bar here, right? So I want to hold a weight. Okay. So to be able to hold it, I can have 2 person, right, hold it, or I can have a cable just hang there to hold it. So in this case, I have two cables here. All right. So I have the one cable. This one is A. Make it easy. I say equals 1. And this is a cable different, the same material, but let's say equals 2. I can make it 3. This will be 2. I don't like 1 because 1 it will disappear when you do the calculation. Sometimes you don't get the point. All right. So we have two cables of different size, but they're the same material. So we know the sigma y. I will use the same value, 200 megapascal. Okay. So, all right. And I want to check. So basically, for ideal design, all right, we want a safety factor of say 2, right, or 4, right? You give a number. Let's say we want a safety factor of, let's say 4. We use the same. Okay. So now applying this load here. All right. So my question is, if I apply this load here, it will share by these two cables for sure, right? You all agree on that? And then, are these two cables safe enough to carry this 100 pounds? Let's make it 200. Newton, yeah. Make it easy, just all Newton. Okay, these are millimeters. Millimeter square, that's the area. Okay. Is this structure safe enough? That's my question. How do you determine is this safe enough? It's not in the center. It will be, let's say, we'll make this part 2 meters long, this part 1 meter long. So it's in the 1/3 of the middle distance from one end. Okay. How do you check if it's safe enough? How do you think? What you should do? Let's say before how to do it. What you should get to be able to check on it? What's your goal to find? What's something that's your goal to find to be able to check on this safe enough? You want to find the stress in the cables. That's the goal, right? Then you can compare it to the safety. Because we know from here, immediately you find out the sigma allowed, right? That equals to sigma y divided by 4. And you know, so it's 50. So basically, we want to find out the stress. Are they below 50? Then we're safe. Are they above 50? Then we're not safe, right? So that's the goal, what we try. Okay, now next, how can you find the stress here and the stress here? Make a cut, Freebody diagram, right? Okay, so where you make a cut? What are you looking for first? You're looking for sigma 1, sigma 2. How can you get sigma 1, sigma 2? You need N1, N2, the internal force, right? So I need to find the internal force in cable 1 and cable 2. That's my objective. Therefore, how can you make the first force and the second force show up? You make a cut there. So the reason I'm making cut there is I need to find the force inside. Okay, so we make the cut. That's the rationale. Why you make a cut? Why don't I make a cut here? Right? That's the rationale. Okay, so I make 2 cuts here. Once you make a cut, this is your free body. Okay, so you have a P here, then you have this part of the cable, and then this is the N1. And this is the second part of the cable, and then this is the force we don't know, we just call it N2. I use N, I don't use P. You notice that? The reason is I want you to distinguish the internal force versus the load. I want to emphasize, make sure your mind, you need looking for the internal force. All right? This tension, I don't know. I assume it's tension, right? I'll find out if it's negative, then it's not tension. But based on my intuition or your intuition, it should be tension or compression. It should be tension, right? You find something there, it's never compression, right? All right, if some 2 guys stand there to support this bar, then it must be compression. All right. Okay, so now this is a free body diagram. Okay, what's next? Equation of equilibrium. All right, so equation of equilibrium. Okay, what's the equation of equilibrium? Now this is a typical example, right? So you can have, this is a 2D situation. So you have sigma fx equals 0, sigma fy equals 0, and sigma m equals 0. Or you can have MA equals 0, MB equals 0, MC equals 0. So whatever the combination, you have 3 independent ones. Okay, so what's the easy one here? Sigma Fy equals 0, right? What about sigma Fx? There's nothing there, no load, so automatically everything's 0. Sigma Fy equals 0. Translate it. So you have N1 plus N2 minus P equals 0. But I can now solve it. 2 unknowns. So I need the third equation. Sigma M to anywhere. Where? To point. This is the A, this is the C, this is the B. To which point? A. Okay, let's say A equals 0. Okay, now translate it. Or you translate it out. To point A, what's the moment?
N2 times 3.
N2 times basically 3. That's the AB part, right? This equals 3. And then,
Minus 2.
okay, so then minus P times the AC part, and that is 1, right? Equals 0. So from here, can you find the N2?
Yeah.
Okay, so you get N2. What's N2? N2 equals what? P over 3, right? Okay, so that's 200 divided by 3. What's the number? 66.7, right? Okay, now what's N1? You just 133.3, right? Okay, now can you find the sigma 1? Sigma 2. Sigma 1 is 133 over 2, right? What's sigma 2? 66.7 over 3. So what's this one? There will be 133 divided by 2. What's the number? 66.7, right? Okay, now I found the sigma 1 equals this much m part. Is this safe? Okay, what's this one? Is this one safe? Yes. So one safe, one not safe. Is the structure safe? No. So we got the answer. It's not safe.
Can you go back?
Go back? Oh, sorry. All right. Okay, so now we know the structure is not safe. Now next question. How can you make the structure safe? Come up with a design, change the structure, make it safe. Right? You can do that after the class. All right?